Welcome back to our session on measuring information transfer in complex systems. In this short video, I want to give you a brief introduction to our activity on measuring local or point-wise information transfer in cellular automata. You should remember from our previous session on information storage when we talked about cellular automata as the most important canonical complex system for considering how information is processed in complex systems. We talked about how discussions around information processing in cellular automata centered on the computational role of emergent structures. In particular, we talked about how domains and blinkers were conjectured to represent information storage, how particles, gliders and domain walls, being particles, were conjectured to represent information transfer, and collisions to represent information modification. We can see these emergent structures much more clearly in filtered dynamics of CAs rather than raw CA values. This was one way of filtering. We looked at another way of filtering in our previous session using information storage, using local or point-wise values of active information storage at every point in space and time in the CA to look at the information storage dynamics. And there we saw that domains and blinkers were indeed the dominant information storage entities. So here in our activity, we're going to try out our transfer entropy estimator on cellular automata data. What we're going to do is use the appropriate embedding length determined previously for the active information storage. We're going to take what was determined there using one of the criteria that we looked at before. We're going to take that embedding length and use it directly for the transfer entropy. Because as we said, we got the same concerns when we pick the embedding length for the transfer entropy as we do for the information storage. We're then going to go on to compute the local transfer entropy values in every point in space and time across the CA to see whether that conjecture is right, whether gliders do indeed have stronger information transfer values than the background domain. I'm going to give you a little spoiler alert here. I'm going to tell you what the results are. If you don't want to see that until you've tried it out for yourself, and indeed I advise you to give it a try yourself first, pause the video here, give it a try, and come back. Okay, so if you're still with me, I'm going to assume that you want to know what the results are. So it shouldn't be a surprise what the results are. I've dropped hints enough times through this and previous sessions, I guess, that the gliders are indeed the dominant transfer entropies in cellular automata, and that is revealed by transfer entropy. As we can see here, we're in our two bottom diagrams. Our bottom diagram on the left here is looking at transfer entropy to the right. Our diagram on the right is looking at transfer entropy to the left, and we can see that here right moving gliders are highlighted as having very strong information transfer entropy to the right, and left moving gliders are highlighted as having very strong transfer entropy to the left. So that is exactly in alignment with the conjecture about the nature of information transfer in cellular automata. And the results make a lot of sense, because at the gliders, what is happening is that the background domain patterns are being broken. If we follow temporarily one given cell, what we see happens is at the gliders that pattern gets broken. The past is no longer predictive of what's coming next. What does help you predict what comes next is the previous value of the glider at your neighbor. So here for a glider that's moving to the left, the background becomes unpredictive. In fact, it becomes misinformative, as we can see in the active information storage plot. However, the source in the glider that was about to come in, if we look at the source, it tells us that we're going to get that particular state in the context of the past, and that's why there's a very strong information transfer there as measured by the transfer entropy. Our next short video, the final one in this session, is going to look at higher order or multivariate versions of the transfer entropy and how we can understand them in relation to the pairwise version that we've already looked at.